Hi everyone. Today we're going to be beginning our new notes, which is on Unit 3, which is Polynomials and Rational Functions. We begin with Section 3.2, which is Polynomial Functions and their Graphs. We'll start by looking at end behavior and seeing what's going on with the function as we move to the left and as we move to the right. We're going to find this algebraically first. So we're going to describe end behavior using a new notation that we're going to call limit notation. The end behavior of a function describes the characteristics of a function for very large positive and large negative values of x. And we look at limit notation. So the left end behavior can be modeled this way here. This would read as the limit of f of x as x approaches negative infinity. And what this is saying is as x approaches negative infinity, as we move to the left in our graph, or as we decrease x, we wonder what goes on with the function. What's happening with f of x? Does it approach a finite value? Does it approach infinity? Does it blow off to infinity? Does it approach negative infinity? What does the function look like on the left-hand side? Likewise, on the right-hand side, this would read the limit of f of x as x approaches infinity or positive infinity. What's going on the right-hand side of the graph or the right-hand end of the function? Okay, so let's go ahead and graph some of these functions on our Inspire. We start off with y equals 4x squared minus 3. So go ahead and take out your Inspire and open up a new graph. So we're going to start with 4x squared minus 3, and let's see what that looks like. So I noticed that on the left-hand side, if I were to zoom out, this function would continue and hold the same shape. We know that the left-hand side, it continues up, it increases as x approaches negative infinity. So as we move to the left, the function keeps going up. And as we move to the right, as x increases, we see that the function also increases. So we see that in both directions, the function is increasing indefinitely. So therefore, as x approaches negative infinity, f of x approaches infinity. And this is what these little arrows mean here. It's saying what value is this value approaching. So we're saying x is approaching negative infinity, just means as we move to the left in our graph. And x approaches positive infinity as we move to the right, or as x increases. Okay, so number 2, here we have the cubic function, x cubed minus 2x minus 2. So we'll go back to our Inspire. I'm going to open up a new function. So we have x cubed minus 2x, and then minus 2. And I'm going to hit enter, but I also want to hide that first one. So I'm going to go back to the first one and just uncheck it. All right, so now we have, this is our second function. I notice that as x decreases, as we move to the left, the function decreases as well. As we move to the right, as x increases, the function increases as well. So we can say as x approaches negative infinity, the function approaches negative infinity. And as x approaches positive infinity, the function approaches positive infinity. Let's graph the next one. Y equals x to the fourth minus 2x squared minus 2. X to the fourth minus 2x squared, and then minus 2. And I want to turn off the visibility for that one. Okay, so now we see our third function here. This is a quartic or a fourth degree polynomial. As x decreases, the function increases. As x increases, the function increases. So we see as x approaches negative infinity, the function approaches positive infinity. As x approaches positive infinity, f of x approaches positive infinity as well. All right, so last one here, we have x to the fifth minus 3x cubed minus 2. This would be a quintic polynomial. So a quintic trinomial to be specific. So let's go ahead and toggle this one off. And then we'll type in the next one, x to the fifth minus 3x to the third minus 2. And so we see this quintic in pink. As x decreases, the function decreases. As x increases, the function increases. So as x approaches negative infinity, the function f of x approaches negative infinity. And as x approaches infinity, f of x approaches infinity. Okay, so to summarize, which of these are odd degree functions? So remember, the degree of a polynomial is, when written in standard form, it's that highest power, or the power of the first term. So which of these graphs between 1 through 4? Odd degrees, we see graphs 2 and 4. So number 2 and number 4. Which are even degrees? So we're looking at the quadratic here, and we're looking at the quartic here. So this would be graphs 1 and 4. I'm sorry, 1 and 3. 1 and 3. All right, so what do you notice about the end behavior of even degree functions? So when we look at graphs 1 and 3, what do we notice about the end behavior? Well, they're going in the same way. They're both going to positive infinity. So both ends go the same way. The same, we'll say, direction. And for odd degree functions, let's see, those are graphs 2 and 4. So looking at these graphs, it looks like they're going in opposite directions. Okay. So let's take each of these graphs and then let's make the leading coefficient negative. Let's see what happens. So if we go back, let's go back to that first one, the quadratic. So I'm going to toggle this one off and we'll go back to the quadratic. So what happens to the graph when I make the leading coefficient negative? When I hit a negative here, well, it flips the whole graph. Now the whole thing is opening downward. We see that the end behavior flips from both going up to both going down. Let's see if that's the case for the quartic. So we'll go back, we'll toggle the quartic. Notice both ends are going up. If I make this a negative leading coefficient, we see that, yes, both ends go down. Okay, so we can see that for even degree functions, both ends um, go downward. Okay, so what do you notice happens to the odd degree functions? Let's see. Let's go back to the odd degrees. Let's go ahead and turn off those even degrees. And let's go ahead and make those odd degrees negative. So our red one here, oh, we got to toggle it on. There we go. So we can see, let's actually go back to the original and see what it looked like. So this is the original. The function is generally increasing. We're going from negative to positive infinity as x increases. And then if we put that negative leading coefficient, let's see what happens. The left end behavior is it's approaching positive infinity, and the right end behavior is it's approaching negative infinity. So those flip as well. Let's see if that's true for our pink function here. So here's the original, same idea as the cubic, but when we make the leading coefficient negative, we see the same to also be true here. So what happens to the graph of odd degree functions? The left end approaches positive infinity, and then the right end would then approach negative infinity. Okay, so we're going to use that new notation, that arrow, to denote that it's approaching. All right, so now let's talk about the dominant term rule. This term with the leading coefficient is known as the dominant term for the end behavior. So in polynomials, it's always going to be looking at the term with the largest degree, okay, or the largest exponent. So let's see, using a table of values, let's see if we can see this dominant term rule at play. So here we have f of x equals 2x cubed plus x squared minus 6x. Okay. If we were to create a table of values, so x and f of x, if we plug in values for x like negative 100, negative 50, 70, and 100, let's see what these terms evaluate to. So for the negative 6x, that last term, we see that we've got 600, 300, negative 420, and negative 600. So these are relatively large values, or I should say relatively small values, because we'll see some larger values coming up. So x squared, plugging in negative 100, we get 10,000. Negative 50, we get 2,500. Plug in 70, we get 4,900. And 100, we get 10,000. And then finally, that cubic term, 2x cubed, we get negative 2 million, negative 250,000, 686,000, and 2 million again. So we've got these really large values for this cubic term, and relatively small values for that negative 6x term, the linear term. So we find that when we evaluate the function f of x and we combine all these terms together, what does the function actually evaluate to at negative 100, negative 50, 70, and 100? Well, we see that these values are really close to if we were just graphing 2x cubed. Like, notice these are not far off at all. Negative 2 million and negative 1.99 million are very close. Relatively speaking. Same thing with like negative 250,000 and negative 247,000 and so on. We can see that these values are relatively close to one another, certainly much closer than these other two terms are when we evaluate the function. So we find that this leading term, this leading term, 2x cubed, has the greatest effect on what the function evaluates to. And this is what we call the dominant term rule. Okay, so which term best models the right side end behavior? So the right side end behavior would be 70 and 100 as x increases. We see that the closest would be, relatively speaking, would be the 2x cubed. And likewise for the left end behavior, that's our negative 50 and negative 100, also the 2x cubed. Similar methods can be used even if all the terms are not power functions. So we see in this next example, we've got a cube root term and we've got a trigonometric term here. By analyzing the function term by term, we can determine which is the dominant term on the left and right side of the function. So let's take a look at each of these terms and determine the end behavior for both the left and right hand side for each of these terms individually. So we'll start with the first term, negative x squared. This is a quadratic with a negative leading coefficient. We know that both ends for a quadratic are going to be going in the same direction. Because the term is negative, we know that they're both going to be approaching negative infinity. So we can write this as the limit of negative x squared as x approaches negative infinity is equal to negative infinity. And then the right end behavior is the limit of negative x squared as x approaches positive infinity, that right end behavior approaches negative infinity or equals negative infinity. Next up, the cube root term. Here we have that S-shaped graph. So we have the limit of the cube root of x of as x approaches negative infinity is equal to the left-hand end behavior is approaching negative infinity. And then the limit of the cube root of x as x approaches positive infinity is equal to positive infinity. And finally, the negative sign of x. Remember, the sine function oscillates between negative 1 and 1. We've got that wave pattern here. So because this doesn't approach infinity or negative infinity, nor does it approach a finite value, we can say that the limit of negative sine x as x approaches negative infinity. Remember, as we keep decreasing, there doesn't appear to be a pattern or a finite value that this function approaches. So we would say that this limit does not exist, or DNE. Likewise, on the right-hand side, the behavior is the same. The limit of the negative sign of x as x approaches infinity does not exist. Okay, so let's go ahead and graph this and see which of these terms is the dominant term based on the end behavior. So if we go to our calculator, we'll go ahead and type in, we've got our negative x squared, and then we have plus the cube root of x. So I'm going to go to my catalog and get the cube root of x. And then we have minus the sine of x. Okay. If we take a look at this graph here, we can see that it just keeps going down, right? As x decreases, the function also decreases just indefinitely. So we see that both ends are approaching negative infinity. Therefore, based on the behavior of each of the terms, we see that the negative x squared is the dominant term. So we can say that the limit as x approaches negative infinity is negative infinity, and as x approaches positive infinity, the limit is negative infinity. All right, so now let's take a look at each term in this next function. Here we have f of x equals e to the x plus 1/4 x squared plus 12 cosine x. So we've got an exponential term, a polynomial term or a quadratic term, and then a trigonometric term. So let's start with the exponential term, e to the x. Now the left-hand end behavior, we know that this is an exponential function. In fact, there's a horizontal asymptote for this function. On the left-hand side of this graph, we see that the function is approaching that finite value, the asymptote. So the limit of e to the x as x approaches negative infinity is equal to that finite value, 0. The right-hand end behavior, it blows up to infinity. So we see that the limit of e to the x as x approaches positive infinity is equal to infinity. For the quadratic term, because we've got a positive coefficient, we know that both ends are going to be going up. So we have the limit of 1/4 x squared as x approaches negative infinity is equal to positive infinity. And the limit of 1/4 x squared is, as x approaches positive infinity, is also equal to infinity. Okay? So both ends are going upward. And then finally, similarly to the last one, this trigonometric term, the 12 cosine squared, 12 cosine x, we know that this term is going to oscillate between negative 12 and 12. The amplitude of this cosine function is 12. Because it doesn't approach infinity or a single finite value, then the limit of 12 cosine x as x approaches negative infinity does not exist, dne. And the limit of 12 cosine x as x approaches positive infinity also does not exist. Okay? So let's go ahead and graph this and see what this looks like on the graph. So here we have, I'll go ahead and replace this. So we have e to the x. Now remember, instead of just typing in the letter e, you have to use this numerical constant e. So e to the x plus, control divide, 1/4 x squared, and then plus cosine x, 12 cosine x. And we see what this looks like. So we can see, let's go ahead and zoom out a little bit. So I'll go to menu and we'll go window zoom. And I'm just going to zoom out a couple times and see what this graph looks like. So I can see that we have on the left-hand side, as x decreases, the function increases. And on the right-hand side, as x increases, the function increases as well. So we see that the dominant term, based on the end behavior, must be that quadratic term, the 1/4 x squared. So we can see graphically that the limit as x approaches negative infinity is positive infinity, and the limit as x approaches positive infinity is also infinity. All right, so these have been our notes on polynomials, specifically end behavior and the dominant term rule. We talked about polynomials and even degree and odd degree. Even degree, the end behavior in both directions is the same, whereas odd degree, they're in opposite directions. Putting a negative coefficient is going to flip the end behavior in both directions. And then finally, we talked about the dominant term rule, which is saying that if a polynomial is in standard form, that first term or the greatest exponent is going to affect the end behavior of the graph. Okay, so we even tried this with other types of terms, so exponential terms, radical terms, trigonometric terms, and we found that the end behavior for each of those terms are also going to be determined by the dominant term rule. Okay, all right, so these have been our notes. We're going to get a lot of practice in class, so we'll see you tomorrow. Have a great day, everybody. Goodbye.